I would like to tell you this evening about 17 elements which caught my attention when I was a graduate student because of their names and because nobody else that I spoke to seemed to know very much about them. Names like lanthanum, like praseodymium, like dysprosium, like holmium. They were names which seemed incredibly evocative. In fact, romantic in a strange sort of way. Nowadays, there's geek romance, and they certainly fell in that category. And few at the time, I think, had heard of them. Nowadays, I think the name neodymium is something that echoes with some people. But certainly, 20 years ago or so, there were very few people, apart from chemists, really. And even those, it was kind of a niche interest. And they were so, in a sense, exotic that people made jokes about them. And here's a cartoon from Sidney Harris in The American Scientist showing two old-time prospectors, right, saying, "Got any rare earths?" Well, it just goes to show, right, that even scientists sometimes joke about the exoticism or kind of weirdness of each other's interests. So I started an independent research career and I did some chemistry with the rare earths, and perhaps I'll get a chance to tell you a little bit about that later on. But you cannot imagine my astonishment about 2.5, 3 years ago, when suddenly mention of the rare earths appeared on the front pages of every newspaper. Here is the BBC saying rare earth minerals shortage, right, feared by the EU and the US. The FT had it on the front page, the Telegraph, the Guardian, all of them were talking about rare earths. And rare earths suddenly became something that, people were talking about. And to those of us working in this area, it was just unbelievable. What was going on in the world? And the thing that was going on was quite noticeable for people's research grants, because suddenly many of our starting materials increased in price very, very substantially. And so what I want to do is to tell you a little bit about these rare earths, what they are, where they're from, why you should care, perhaps whether you should invest. And by the end, I hope I will have told you, or I will have convinced you, that actually, even in those small little corners of science, there's all kinds of interesting, strange stuff, which in the long term, by these strange ways, actually comes to fruition. So the first thing I have to do is to say the rare earths. You know what? They're not rare and they're not earths. It's an old word, earth. Earth is a word that goes back a long time. And what it really does is, I should draw attention to the fact that these elements, which are here in this periodic table, and you can see that it's being distorted slightly to really highlight that group of elements. Earth means an element which is like these guys over here, and generally an oxide. And when you dissolve either the element or the oxide in water, you tend to get an alkaline solution, or certainly there are things which react with acids. And when we think about rarity, here are the abundances of the elements in the Earth's crust. Now, on the top left-hand side are that real common as muck stuff. The stuff of your garden, the stuff of your house, the building, the structural materials, oxygen, silicon, aluminium, calcium, iron, titanium, magnesium. There's carbon And you can see on the left-hand side that the scale is logarithmic. In other words, each time you go up by one step, you've gone up by a factor of 10. So what we're really saying is that when you go from here to here, you're actually talking 1,000,000 times more abundant. I'd just like to take a quick straw poll. Anyone wearing gold here today? Put your hands up. Yeah, there's a few of you. Anyone wearing platinum? A couple of people. Don't know. Let's have a look down here. There might be a few people wearing silver. Notice that silver is a lot more abundant. But down here are the rarest metals, and they're the ones that we often associate with sort of expense, right? And these rare earths, they're not that rare. Look at them. Here they are highlighted in blue, and we include yttrium on the left-hand side, and the reason for that will become obvious. Along here, this is essentially how deep you're drilling down into the periodic table. And you can see that this stuff is as common as tin. It's as common as lead. It's as common as copper, as zinc, as chromium, nickel, cobalt. You know, the stuff that is really common that we use in everyday applications. And so these things aren't rare at all. They're actually surprisingly common. So how is it that they came to be called rare? And for that, we have to travel back about 200 years. We have to think back to a time when, in many ways, a lot of what was going on in science was what Rutherford would, in rather dismissive, disgusted fashion, refer to as stamp collecting. It was the idea of going out and looking at the world and finding new stuff and perhaps classifying it. So Linnaeus in Sweden was looking at organisms and dividing them up into classes, into categories, identifying things that were related to each other, kind of making these connections and slowly making sense of the world. At the same time, there were chemists who were analyzing stuff and slowly, gradually finding that you could boil materials down to individual elements. And the end of the 18th and the 19th century are this incredible heroic age of elemental discovery. At the same time, there are people going out doing amateur geology, picking up rocks and saying, what is this stuff? Can I find out what it is? And a young army officer by the name of Carl Axel Arrhenius, we know next to nothing about him. The only thing we do know is that he picked up a rock in a place here on the island of Vaxholm, near the village of Utterbu. Not Ytterby, Utterbu, I'm told. It was a fluorspar mine, and he picked up this rock, and he was quite amazed because it was incredibly dense. It was one of the densest things he'd ever come across. And only recently, another element, an element called tungsten, which means the heavy stone, had been found in that part of Sweden. And he wondered whether this might be a mineral which, too, contained this heavy stone, this tungsten within it. He did some analyses and quickly gave up. He didn't know what it was. It just didn't fit anything. And so he got in touch with one of the great Swedish chemists of the time. Now you have to remember that Sweden in those days was Greater Sweden, and it included, over the Gulf of Bothnia, what is now Finland. And so he got in touch with this man, Johannes Gadolin. And Gadolin was an analyst and a chemist, and there are really two things for which he is remembered. The first thing is that, like most good Scandinavians, he seems to have taken an interest in distillation. Although I must point out that there is an indication that Gadolin was actually not much of a drinker. Nevertheless, he came up with the idea of water cooling a still so that you could collect the alcohol more effectively. And he built one of the first water-cooled condensers. This has come to be known as the Liebig condenser. It's not. I would argue that it's the Gadolin condenser. Gadolin analyzed this rock, and try as he might, he dissolved it up in acid. He filtered. He did all the standard operations. He tested it for every element that he knew, and he couldn't figure out what it was. And in the end, following on from Sherlock Holmes, when you've tried all the possible things, you are left with the impossible, and that was that it was a new element. And so he named this element yttrium in honor of this place, Ytterbu, and he named the material that he got ytterbia after that. And this is really the beginning of one of the great chemical shaggy dog stories. Over the next 100 years, chemists would literally go mad trying to figure out what these damn things actually were, desperately trying to separate one from the other. And this diagram tries to capture that. And you can see in orange when people claimed to have found a true element. And then you can see those circles in yellow underneath where actually other elements were found within them, sometimes 2, sometimes 3. In the end, they found 16 different elements, and it would take a very, very long time. Now, you might say, but what's the problem? Why would these 16 elements be so difficult to separate? And the real problem is this, and this is the first of a series of incredibly trivial demonstrations. The real problem with these rare earths was the fact that in terms of chemistry, their properties were extraordinarily similar. And so what I'm going to do is I'm going to do a classic reaction of the lanthanides and or rare earths, because the names are almost interchangeable. And I'm going to add a little bit of sodium oxalate to a solution, in fact, a mixture of lanthanides. And when I do that, you will see immediately that a precipitate forms. Tremendous demonstration. Yeah. I knew it, yeah. I can assure you that it's going to get worse. The problem that the chemists faced was the fact that every single one of these elements would undergo a reaction like that. That to a very, very good degree of approximation, all of these elements were the same. That if you added fluoride, they would all precipitate. If you added oxalate, they would all precipitate. If you tried to crystallize them. And remember, there were very few tools available to chemists at the time. What could you do? You could boil a rock up in acid and dissolve it. Then you could filter it. And then you could add a reagent to precipitate stuff, or else you could boil down the solution, concentrate it, and then grow crystals by cooling that solution. That's all they could do. And so here is the method by which they started to try and separate these elements, which was to essentially take an original solution, boil it down. You would then get crystals at the bottom of your beaker. You would pour off the supernatant into another beaker, take your crystals, dissolve them up. You would then boil them down, separate them into crystals and solution. Meantime, you'd taken this one, you'd boiled it down, get crystals and solution. And for the two elements here, ytterbium and lutetium, their separation required a French chemist called Urbain, 15,000 crystallizations. That is dedication. These guys knew that this was an interesting problem that would one day really add meaning. And I should mention that you look at this discovery timeline, right? And you start here, right, at the beginning of at the end of the 18th century when yttrium and cerium are found, and then slowly all the others come out. You're talking about well over 100 years for the separation of these things. It really is extraordinary, and nowhere else in the periodic table is there such an incredible timeline like this. Well, it wouldn't be long before people would start trying to find applications. And one of the first was found by a man called Auer von Welsbach. Auer von Welsbach was Austrian, and he went to work with Robert Bunsen. We'll hear about Bunsen in a little while. Bunsen was an excellent chemist who contributed to all kinds of areas. And sadly, his memory is completely trivialized by the Bunsen burner. We will hear more about what he really did later on. But what Auer von Welsbach was able to do was to actually separate praseodymium and neodymium. They had been known, they were thought to be a single element, which had been named didymium. Didymium means from the Greek word for twins. And fortuitously, the twins turned out to be two elements. Praseodymium, the green twin over here, and neodymium, the new twin there. Well, he was not simply interested in science, he wanted to make business. And so he thought, what can we use these for? And he managed to smelt the elements, and then he was able to alloy the mixture of these rare earths with iron. And what he got was a metal that he called Auer metal. Here it is, and I'm going to strike it. And you can see this stuff sparks amazingly. This would completely revolutionize smoking. But it would also mean that you could light fires quite easily. The cigarette lighter, right, would of course end up all over the place. You could light things. And so that was quite tremendous. And it's very important to think about this stuff because you saw how bright those flashes are. That means that when we strike this, we get an incredibly high temperature. And that speaks to, on the one hand, the extraordinary reactivity of these rare earths. They tarnish easily in air. They react, quite violently if finely divided. They burn like crazy. But the flip side of that is that once they've burnt and you've made the oxide, that oxide is incredibly robust and stable. So the rare earths turn out to be really good for making ceramics. And Auer von Welsbach thought this is quite interesting, and he went one further. And what he did was he came up with a means of lighting the world. And I'm going to try and see if I can get this to work. This is untested tonight because I lost my old lamp and I've sort of had to quickly get something else. But what I'm going to do is I'm going to turn the gas on. And of course we know that gas doesn't give out much light. But if we just light this, and I hope it's lit, did it actually light? Nope, not quite. There we go. It's going to light. Now, this is cotton, which has been impregnated with a number of different reactive metals, okay? But within these, in some of the formulations, there is cerium. And you can start to see that very quickly, once this is burnt off, the cotton burns away, leaving behind a framework of this incredibly stable, rock-like ceramic. And the ceramic glows. It glows absolutely white-hot. This is the way in which the streets were lit all over Europe by gas lamps, was by exploiting this phenomenal thing, the gas mantle. I had hoped that I would be able to tell you that this lecture theater, as you can see here, when James Dewar, shortly after that, the painting is just outside the door there, was lecturing here that they'd used gas mantles. But in fact, this lecture theater was not lit with the rare earths. Frank James here has told me that this was the first theater to actually be lit by electric lights. And that was von Welsbach's great competition with Swan and Edison. And in the end, Swan and Edison won out, and the gas mantle was actually left really for campers. And very useful it is too. Having spent many years in Kenya, we used to use these. They're great. So let's get back to the rare earths. Where do the rare earths come from? Well, of course, you dig them out of the ground. And what you find is there are a whole pile of deposits, really all over the world. And these are the two major minerals that are mined, Monazite and Bastnaesite. There are, in fact, a whole pile of others. If you go through a mineralogy text, you'll find all kinds of silicates and fluorohydroxide and so on. But here we have monazite, which is essentially a lanthanide phosphate mixture. Although it says cerium there, what you tend to find is that these deposits have different compositions depending on where you dig them out of the ground. Some of them produce the early ones in the series, the light rare earths, and some of the deposits produce consist of mostly the ones on the right-hand side of the list. Those are the heavier rare earths. And depending where you dig them out of the ground, you get sort of different compositions. So you have monazite here, which is a phosphate, and on the other hand, you have bastnaesite, which is named after the town of Bastnaes, which is not far, in fact, from Uterbru, which is a fluorocarbonate. Where do you find them? Now remember, I told you they're not rare. Look, you find them all over the place. You can find them in Australia, you can find them in southern Africa. In fact, a big deposit's just been found in Kenya, not far from Mombasa. You find them in China, you can find them up here. You can see that Sweden is even mentioned. Greenland, wherever you look, turns out you find rare earths. And about a year ago, there was huge excitement because the Japanese announced that they'd found some right here on the seabed. Really good deposits of these sands. But more than 90% of the rare earths at the moment come from one place, and that's a place called Bayan Obo in China. In fact, in Inner Mongolia, and this is the place here. And let me show you a photograph that I got from NASA a couple of days ago. And this is a photograph from space of Bayan Obo. This is the town, right, which has about 30,000 inhabitants. And those are the two pits. They're huge. Absolutely enormous. And if you compare this, here's a photograph of the great mine in California, which was the world's major supplier until about 20 years ago. This is a romantic place called Mountain Pass. How they came up with that name, we'll never know. This is about 300 meters deep. These things are huge. And they dig them out of the ground, drive them out by the truckload, and then they start processing the ore. And the processing is quite an involved business. We'll come to see just a little bit of it in a moment. But the real question is, why were they so darn hard to separate? Why are they so similar? And to do this, we've really got to think chemistry. You've got to think like a chemist. And to think like a chemist, you have to ask yourself the question of what determines how soluble something is or how insoluble, how easy it is to crystallize things. And in a nutshell, when you're talking about metal ions, you're down to really kind of one thing, and that is size. Size matters big time. So here is the periodic table, as we've seen, with lanthanum on the left, lutetium on the right, and here is the series. And you can see that between lanthanum and lutetium, there's a change of less than 10%. And you've got this incredibly smooth gradation as you go from the left to the right. And what this means is that the solubility of one relative to the other is only going to be 1% different, if you're lucky. The other thing is that although yttrium sits one place higher in the periodic table, look at its size. It's got a radius of about 1.2 angstroms, and that places it right here so that it's always mixed up with holmium and erbium. They always come together. And so geochemically what happens is that you tend to get deposits which concentrate these guys, and these guys tend to be too soluble or something. And then you get deposits where these guys crystallize out, and those ones don't get a look in. And so you have deposits in different parts of the world which have more or less. So how on earth did we get to the point where we could actually separate stuff? And finally, I can tell you that you can thank the Manhattan Project for something. Because most of you will, of course, think of the Manhattan Project as being the great project to produce the atomic bomb. And you will probably think the Manhattan Project basically involved a place called Los Alamos and then a place called Alamogordo, where they actually set off the first sort of bombs, where they tested the first things before they used them in anger. But actually, there was a huge network of labs across North America where different things went on. And some of these will be familiar to some of you. You may have heard of them. I want to focus on two places. One is the Ames Lab, which is in one of the flattest places in the world in the middle of Iowa, and over here in the hills, Oak Ridge in Tennessee. So the question was, how could you do the equivalent of all of those crystallization, separation steps, instead of having to do it, manually? How could you automate the process? And someone came up with a brilliant idea. And the idea was to use what's called ion exchange. Now, ion exchange is something that is very, very simple and very, very cunning. And I have here on the left, you can see here this tube, this column, which contains an ion exchange resin. And it consists of these tiny orange beads, and those beads are made of essentially polystyrene. And the polystyrene on each of those benzene rings, you've got a sulfonate group. And the sulfonate group has a charge, so it's negatively charged. And if it's negatively charged, it's kind of interesting because that means that the positively charged rare earth ions, lanthanides, are going to stick to them. Now, how much will they stick? Well, it's going to depend on the ratio, essentially, between how charged they are and how big they are. The big ones aren't going to stick very strongly. The small ones are going to stick more strongly. And so what you do is you pour a slug of your mixture up at the top of this column in here. You then start draining the liquid through, and you help it with loads of usually dilute acid or something like that. And what you find is that gradually out come the larger ones first, then the middle ones, and then the small ones. And it was all down to really the efforts of a man called Frank Spedding. He's a brilliant, brilliant chemist who became obsessed with the rare earths. And he came up with this method. And it was extremely important to the Manhattan Project and afterwards, because what it allowed them to do was to do very rapid analyses of fallout products, of the things that were produced in their experiments, and to find out, what was in those mixtures. And here is one of the original papers, and you can see that the yttrium and I can't read from this angle, I'm afraid. Anyway, you can see that there's erbium, and there's holmium, and there's thulium, and there's ytterbium, and there's lutetium. Anyway, and they can be separated out very, very nicely. Now, if this sounds a little bit exotic, let me just point out that these ion exchange resins, you have one in your house, right? This is the water softener that sits in your dishwasher. And what the resin does is it grabs hold of the nasty 2+ magnesium and calcium ions and releases sodium. That's why you pour the salt in to regenerate. When you pour the salt in, you swamp it with salt, and that releases the calcium and magnesium. But essentially, you're doing the same thing that Spedding and his friends were actually doing. And they were able to get hundreds of grams of rare earths at a time, and suddenly you could start doing stuff, right? You didn't have to spend 5 years desperately trying to get isolate them. But meanwhile, their competitors over at Oak Ridge came up with a better idea. And they used what's called solvent extraction. And what they did was they found a way to, by adding this phosphate, to actually get these ions, even though they're charged, to dissolve in kerosene as well as in water. And they would separate, they would partition between the kerosene and the water, in fact, nitric acid and kerosene. And the extent to which they did so depended on how large the ion was. This now gave them not a batch process where you pour it in at the top, run it out, but actually a continuous process. And so you could run stuff in one of these tall towers, and the kerosene would sort of float up, and meanwhile the nitric acid, being denser, would come down. And in doing so, you could start to separate literally kilogram quantities. And for the chemists here, can you imagine the idea of getting a paper in JACS in which you report, right, in the Journal of the American Chemical Society, the first kilogram of gadolinium oxide? Absolutely astonishing. Now you could do things, and the lanthanides were extremely interesting. In fact, the interest had first, in many ways, been sparked by Robert Bunsen. Now, Robert Bunsen, you all think of the Bunsen burner, but Robert Bunsen is a towering figure in 19th century chemistry, because alongside a physicist called Gustav Kirchhoff, they had the idea of taking the light from a flame and putting it through a prism and redoing the Newton experiment, but instead of using sunlight, they would actually use it to analyze, right, what the chemical composition was. And they discovered that each element had its own specific signature, This was spectroscopy. It was the beginning of spectroscopy. And Bunsen and Kirchhoff came up with this idea, and at the same time, people were looking, particularly Fraunhofer, had looked at the spectra from the light from the sun, and they suddenly realized that there was a correspondence between the elements that you could see in a flame on Earth, and you could see the same kind of light, of patterns in the spectra in light from the stars. What was incredible was that it suddenly unified the universe. Right? The universe was one place. Everything in the universe is made of the same stuff. And it's all thanks to this guy, Robert Bunsen. Now, Bunsen started taking these rare earths. He was obsessed with them. And he started putting them into and making little sparks with them and recording laboriously the spectra that he was getting. And here's a picture of what these spectra might look like today with a modern spectrometer. But really to identify how these things absorbed light. And it took him 7 months to record all these spectra. It was a tour de force scientifically. And at the end of 7 months, he wrote up the manuscript in longhand, beautiful. And he had this manuscript, and he thought at the end of it, I'm going to the pub, going to have a lunch. He put a paperweight on the table, a round bottom flask. And he went to the pub, came back from the pub an hour and a half later. Smell of burning. The sun had come around the corner, and the light had focused through the round bottom flask, and the whole lot had caught fire. He wrote a desperate letter to his friend Henry Roscoe here in London, the chemist, detailing all the horror of it. And he then went back into the lab and methodically redid the whole darn thing. Incredible. These spectra, suddenly people realized that they could absorb light in interesting ways. And one of the people who really picked up on the rare earths the most was a brilliant spectroscopist here in London, a very controversial one, a man called William Crookes. And William Crookes is one of the most high-profile experts in analyzing light that there was. Crookes almost discovered the electron, came very close, and here's a picture of him holding his famous experiment, the Maltese cross experiment, in which he was able to show that these strange rays which carried electric current through the darkness, through the vacuum, traveled in straight lines and could even cast, in a sense, shadows. And so this Maltese cross experiment is depicted in a cartoon drawn by Spy for Vanity Fair. And the caption underneath, which isn't included here, was this wonderful Latin pun based on the idea of the cross, which in Latin is crux, ubi crux, where there's crux, ibi lux, there is light. And Crookes was really one of the foremost people in the study of spectral phenomena. He was actually invited by the Glassworkers Cataract Committee, right, of the Royal Society. And it's kind of interesting that glassblowing at that point had become so important that people were starting to realize that glassblowers were damaging their eyes and developing cataracts. And what Crookes started doing was putting rare earths into glass to be able to filter out the invisible rays that had recently been discovered, the infrared, the ultraviolet, and so on. So Crookes really started putting the rare earths on the map and coming up with new applications. And what I want to do is to show you one crucial application. Now, many years ago, one of the glassblowers in my department phoned me up, knowing that I do a bit of glassblowing, I can fix the odd bit of glass. And as he left, he gave me these glasses. And he said, "You're going to need these." And these glasses are made of what's called didymium glass. Remember that, praseodymium and neodymium mixture. And when you wear them, you look a bit like Dr. Strangelove. But they're incredibly important to glassblowers because what they do is something quite remarkable, and they protect your eyes. And I'm very grateful to Ed Prosser, who is there filming at the moment, who made a little film with me earlier on this year, just before the Christmas lectures. And I'd just like to play you just a little bit, just to show you how incredible these things are. And so if we take these glasses and we actually put them
Between the camera and the flame itself, you'll see how magically the sodium disappears and the spinning glass is revealed.
So, the great thing about videos is that they make you look great. These glasses are extraordinary because you saw that when you put the glass in the flame, there's this incredible orange flare, and that's the sodium ions in the glass which are being vaporized, and they glow very brightly to the point where you can't actually see the glass. Now, what I'm going to do is to show you how this actually works, why it works. And this will really highlight why it is that the rare earths are so special to so many chemists. And what I want to do is to do a little bit of spectroscopy. Now, let me just turn this off so that we go kind of into darkness. And when we bring the lights down, you will see that we're projecting a little spectrum onto the screen here. And what I'll do is I will dip a little bit of copper sulfate in front of the solution. In fact, it's copper sulfate with some ammonia. And you can see that what will happen is that we absorb the entire spectrum apart from the blue, right? And so this is very typical of normal colored materials, is that they absorb very, very broad bands. Let me show you instead what happens when you use the rare earths. So here we go, and watch what gets absorbed. Now remember that the sodium has that yellow-orange glare, right? That infuriating color when you're driving or if you have one of those lights outside your bedroom. And I'm going to put this thing in front, so watch carefully and you'll see. And you can see that there's a shadow which falls in only certain parts of the spectrum. It's completely transparent, but it's particularly dark in the yellow-orange. And so when we take it out, all the light comes through, and when we put it back in, you can see those sharp absorption bands. So this is the really fantastic thing about the rare earths, is the fact that they have these very, very specific absorptions of light, and as we'll see in a moment, very specific emissions. Now, whenever you see light produced or absorbed, what you know is that this is something to do with the electrons, is that electrons are in some way being rearranged within the atom or within the molecule. And so what are the electrons that are involved in the rare earths? Well, the electrons, the crucial ones, are what we call the 4f orbitals. And the 4f, the electrons which sit in the 4f orbitals are the ones which are really responsible for these unusual properties. Now, this is where it gets kind of tricky, because what I need to bring across to you is the strange paradox of the rare earths. Normally, the electrons that give rise to colors in molecules are the ones which are most immediately available. They are the ones which are involved in the chemistry. And so the same electrons which will allow you to change the behavior of your molecule, that you might oxidize, you might remove an electron, you might put an electron back on, or you might sort of use them in bonding or something, those outermost electrons are also the energetically most accessible. And what's very strange about the lanthanides is that the electrons that are involved in all of this optical stuff actually sit. They're buried deep down inside the atom. And there are loads of other electrons which sit further out. And so what this means is that if we think about a lanthanide atom, we normally think of it as being completely spherical. That it's essentially a sphere which has a charge, but there are no directional effects. There are none of the kind of covalent effects, to a chemist, which allow you to essentially make a chemical handshake in one direction. And so the association of a lanthanide or a rare earth with other molecules turns out to be a strangely loose and dynamic one. And here is a typical spectrum, in fact, from some fluorescent lights in our teaching lab, and you can see that each time there's one of those spikes, that kind of corresponds to one of those dark regions that we saw earlier. If we start worrying about how the electrons behave within the atom, we have to worry about all kinds of things. First of all, there's that pesky thing called quantum mechanics. The second thing is that the electrons interact with each other. They repel each other. And because they're buried in the core, they actually interact quite strongly. And on top of that, in order to really understand these things, you can't just use any old quantum mechanics. You have to take into account relativity as well, because the electrons move very fast. And so let me just show you the energy levels for lanthanide fluorides. And you can see here that for cerium, where there is only one electron, effectively you only have 2 levels. When you get to praseodymium, which has 2 electrons, you have, well, let's call it a mess. When you move to neodymium, it turns into a big mess. Samarium here is a total nightmare. And the nightmare gets worse and worse until you get to gadolinium, where things simplify a bit. And they then become messy again. But the crucial point is that the electronic structure of the lanthanides is incredibly, incredibly complex and incredibly demanding of all of the kind of tools that chemists have, physicists have at their disposal. But the great thing is that what each of these mean is that although chemically these elements are very similar, when you start talking about the behavior of the electrons, the light optical properties and the magnetism, each one is completely unique and special. And so we can use them to make light. And I'm going to give you 2 examples. For that, I'm going to turn the lights down a bit. I will turn this off. And what I'll do is come around the table. And what I want to do is just to show you, when we turn on the lights here, that you can get, just give this a second to warm up, try again, and you can see these two elements which light up, they fluoresce really quite spectacularly, right? What they're doing is they're absorbing the invisible ultraviolet light. This is rearranging those F electrons, and then after a little bit of vibration, they then release the energy again in the visible part of the spectrum. And if you, in fact, put the surrounding materials and you arrange them carefully, then what you'll get is you can get pretty well all of these to fluoresce, each one with different colors. How can you use this? Well, I've already mentioned that you can use this in fluorescent lights. You can use this, of course, in laser pointers. And so in here, that green color is actually generated by a crystal which contains neodymium, and that helps to actually double the frequency of the light that is produced elsewhere in the laser. But my favorite application of all is this one. This is a euro banknote, and I want you to look closely. You will see that it glows. Can you see the stars? You may be able to see the stars here at the front. For those of you who can't see the stars, let me turn it over. And what I want to do is show you that you can actually see Europe. And you can see the bridge across the top, picked out beautifully using this fluorescence. And of course, which element would you choose to dope your banknotes with? Well, of course, it has to be europium. And buried deep in the euro currency is a fantastic, a brilliant chemical pun, right? An extraordinary joke that has been buried into the currency at a chemical level. And I have to say, I love it. It's just amazing. We can make light, and of course we can use this light for different things. Now, you all know that much of the internet actually operates using fiber optics. What we do is we have these gossamer thin wires, fibers of glass, and they're incredibly pure glass so that the light will travel for miles and miles. But actually, you know that light doesn't travel for miles and miles, or there's a limit to it, because all we have to do is look up in the sky and see that the sky is blue. And the sky is blue the reason the sky is blue is because of, in fact, Tyndall, whose picture you can see out there, and Lord Rayleigh, whose picture probably is out there as well, who both spent time here at the Royal Institution, and who explained the fact that when you shine light through a medium, you get a process called scattering. And scattering is the deflection of the light through a certain angle, and it depends on which particular kind of scattering you're talking about, and the intensity has angular dependencies. But the crucial thing is that it depends on wavelength. And so blue light is scattered more than red light. That's why you see a blue sky during the daytime, and you see red light at the sunset. But if you want to send light down a fiber for tens of kilometers, you don't want to mess around with visible light because it will be attenuated. And here is a plot which shows you, first of all, fiber optics. These are not internet fiber optics. That's a lie. They've put a torch behind it, but that's not the light, because the light that's used is invisible. Here is the wavelength of the light, and here's the edge of the visible. So this is what we see, right, when we saw that rainbow earlier, right? It was here. 700, we're moving into the near infrared. And this is the attenuation. This is how much the light is going to be sort of scattered, let's say. And as we go down, we go down, we go down. And the minimum comes here around 1500. 1500, 1.5 microns, is the wavelength at which one of our elements emits, and that's erbium. So erbium is crucial for the amplifiers that produce the light that gets fired down the optical fibers that essentially connect our world. And so if in the 19th century copper was the element that linked our whole world together, I would argue that erbium is the element that links us up in the modern post-copper internet. Now, we've talked about light, and I've hinted at magnetism, but of course the other place where the rare earths come into their own has been in magnetism. And some 20 years ago, it was discovered that if you made an alloy of neodymium and iron, then what you would be able to do was to generate magnets which were at least 1,000 times stronger than anything that any permanent magnet that had ever been seen before. And I should perhaps try and illustrate this, because down here I have a small piece of the only sort of, well, I mean, we won't go too deeply into the magnetism side, but the sort of most magnetic, let's say, of the lanthanides, and that's gadolinium. And I'm going to take a typical kind of fridge magnet, ferrite type magnet, and I'm going to try and see if I can get this thing to move. And you can see that I need to bring it in really quite close for anything to happen. Now what I'm going to do is I'm going to take some of these rare earth magnets. And first of all, pulling them apart takes some doing. In fact, let's not. You can hear the way they snap. But if I take these and I start doing this, you can see the distance at which, okay? These things are incredibly strong. And if we take two of these, we can put one on the palm of our hand like that, the other one on the other side, and they will stick rather nicely. If I flip this one over, right, it's really rather cute, right? It's kind of amazing. Didn't Arthur C. Clarke say something like, if you showed people a sufficiently advanced technology, it would appear like magic, and that certainly is. So these kinds of magnets have completely revolutionized our technology. And of course, what they've done is they've allowed us to exploit or even enhance that phenomenon, which some people claim was discovered here at the Royal Institution. It was actually discovered by Ørsted in Denmark, and that's electromagnetism. And now I'm going to be drummed out of here. But of course, Faraday is the person, right, who really kind of put it on a firm intellectual footing. And all of these applications here, right, are essentially derivatives of Ørsted and Faraday. The idea that you have electric motors in trains, that you have regenerative brakes in trains, you have, an awful lot of this neodymium iron boride alloy sitting at the top of the turbine, which is what allows you to generate the electricity. And the crucial thing to remember is that actually the neodymium in this alloy, and there's another alloy, which is called cobalt samarium. Most of the magnetism actually comes from the iron or from the cobalt. And what the neodymium and the samarium are there for is simply to kind of pin that magnetism in place. And then the real workhorse is the iron there. But if you remove one of those rare earths, the whole thing, you lose it completely. And so having the neodymium in place is absolutely critical. And the real problem is that neodymium is not very common. So there are research projects out there desperately trying to use some of the more common rare earths, particularly cerium, in order to be able to sort of reduce the prices of these magnets. And here is the Prius, and the Prius is a triumph of rare earth-based technology. And here's a picture which is based on one from the great American rare earth producer Molycorp. And you can see here the different places where it's used. UV sort of filtering glass, polishing, and of course, cerium, which is cerium oxide, is often referred to as rouge. And rouge has been used to polish telescopes and to polish all kinds of optical equipment for many, many years. Very hard oxide. And you can see here that different components are used in all kinds of places. They are the neodymium magnets. And I've just mentioned this crucial rouge stuff for polishing, and that material is called ceria. Cerium dioxide. It was first discovered by the great Swedish chemist Jöns Jakob Berzelius, who's one of my great heroes, and if you want to hear more about him, you must come to the BBC's Science Top Trumps that we're doing on Saturday in Cheltenham next week. But here is cerium dioxide, and the chemists here will realize that this is no longer a 3+ compound. It's one where the cerium appears to be 4+. And this cerium 4+ material is extraordinary because not only is it very, very hard, very robust, but what you can do is you can use it, and this is the actual honeycomb from a 3-way catalyst from a car that we cut out earlier with, don't know what happens to him, but what it does is it takes unburnt fuel, carbon monoxide, and so on, and what it's able to do is to kind of burn that so that you convert it to less harmful, perhaps, carbon dioxide and water at the end. And this is made, there's a huge proportion of cerium. Without cerium, all of our attempts to clean up the air in our cities, right, is not possible. The function of this cerium is quite interesting because what it's able to do is to flip between the 4+ and the 3+ state. And as it does so, it's able to release oxygen. And so it can pick up oxygen during the rich part of the engine cycle and then releases it during the lean part so that essentially it gets rid of all of the sort of pollutant stuff. And so this begs the question, and very, very briefly, because I'm running out of time, why the lanthanides are 3+. And in the end, what so much of chemistry is about is finding compromises. If you have an energy cost on one side, and in this case it's stripping electrons off one atom, you often get that back by forming a bond with something else, by making some kind of chemical connection. And it turns out that the lanthanides end up normally being 3+ because stripping off 3 electrons is just right, and going beyond that costs you too much. And so you can compensate for that initial cost, and you can get it back through bonding. Now, these 3+ ions turn out to be incredibly useful. Here's one. This is gadolinium, and remember I said to you that this thing is quite magnetic. We can exploit the magnetism of gadolinium ions, and here is the molecule that is injected into patients who go into MRI scans. And what the gadolinium does is it's able to influence the very faint magnetism of the water that the MRI experiment is able to do, changes the lifetime of the water molecules. And in doing so, it allows you to differentiate between water in different regions. And so what elements like gadolinium are able to do is to facilitate things like MRI and improve our ability to do imaging. But let's come back to these 4+ things. Because this question of why cerium might go 4+, it turns out that it doesn't cost that much. In fact, because cerium is off on the left-hand side, so it doesn't cost you too much to strip off that last electron, is something that my friend and colleague Nick Johannes and I started talking about, in fact, it was his idea many, many years ago, to go and take a look at some molecules in which we thought that the cerium was 4+. And the molecule that we chose was this thing here, something called ceracine. And using an X-ray experiment called Zane's, we found something rather peculiar, is that although the molecule seems to behave chemically as if it is 4+, in fact, when you look in detail at its electronic properties, it resembles a 3+. And this was a real paradox, and it's something that we are continuing to kind of work on. Now, these compounds are hard to make. Here is one of the UK's leading lanthanide chemists, Jeff Cloke, who's showing you how you actually work with many of these compounds. They're incredibly reactive with air. We saw the metal actually sparking. These compounds are, in a sense, somewhere between the metal and the oxide, and therefore they're incredibly reactive in their own right. And we chose to look at molecules in which we took one of these metal ions and we surrounded them with some organic groups around the outside. And you can probe where the electrons are by using what's called photoelectron spectroscopy. You shine in light of the right energy to pop out one electron. And you can then measure the energy of that electron to find out its provenance, to find out where within the atom it was actually originally located. And that allows you, if you remember that hideous diagram with all those energy levels, to start picking out the individual energy levels. The X-ray source we use, of course, is synchrotrons. What else? Everybody uses synchrotrons these days. And what you do is you fire electrons around in a circular orbit, and as they get pushed around a corner, what they do is they emit energy. They emit light, they emit brilliant X-rays, and they're tunable. You can get any wavelength that you want. And by choosing the right photon energy, you can actually favor the popping out, ionizing an electron from those metal 4f orbitals, the ones that we're really interested in, the ones that determine whether you're going to go 3+ or 4+. And you can favor that over the electrons associated with all the carbon shrubbery around the outside. Shrubbery, that's a technical term. And what we found was something extremely peculiar and very, very puzzling. In fact, we almost didn't do this experiment because we thought it would be too boring. We expected if you took one electron out of cerium, there was only one way you could do that, that you would simply get a product which was one electron less. And the weird thing was that we saw two. And what this is telling us is that on one level, this ion, right, the product where you've removed the electron, is in a sense, simultaneously, the way to describe it is by using both a 3+ and a 4+ picture at the same time. It's a multi-configurational ion, and the complexities of the electronic structure are astonishing. Now, I have to make it very clear that I am simply the lab monkey who makes stuff, and the intellectual brains behind all this stuff are people like Nick Johannes and Jennifer Green at Oxford, who have really done all the stuff, all the thinking. But the take-home message, in fact, is that cerium dioxide is also a little bit like that. And it owes its virtue to the complexity of its electronic structure. The fact that it, too, is in one of these mixed states, which is a little bit 3+ and a little bit 4+. The rare earths have extraordinary applications. They have turned up in our lives in all kinds of places. This thing here that I was wearing, right? You'll find it in, of course, electronic applications, but even on the surfaces of lenses, you have coatings of lanthanum fluoride and things like that to reduce reflections and that kind of thing. They are completely essential to us. And so when 2-3 years ago, people began to panic because China suddenly realized that it was sitting on a gold mine. And why should it sell? Why should a developing country sell its mineral wealth when instead it could add value, right, by producing whole products together? Then what they did was they imposed export quotas. And they reduced the supply to countries like Japan. There were other political issues too. Of course, there are disagreements about what goes on in the South China Sea and that kind of thing. And this was, in part, a way for China to assert itself and, of course, to favor its own industry. You think your gold that you're sitting on has been profitable. Take a look at this. Here is the price of gold and silver. These are the prices of the rare earths, and you can see that they really peaked in 2011. Yeah, you should have sold in 2011. But you know what? You're still quids in, because look at where they are relative to 100 where they started. The rare earths are amazing. And I think I should leave you with Sir William Crookes, who at a British Association meeting in 1877 said, "These elements perplex us in our researches. They baffle us in our speculations. They haunt us in our very dreams. They stretch like an unknown sea before us, mocking, mystifying, and murmuring strange revelations and possibilities." William Crookes wasn't just a spectroscopist. He was a prophet. The rare earths. Thank you very much.
Thank you, Andrea. That was a superb presentation. I think after the reference to, or the suggestion that it was Ørsted rather than Faraday who discovered electromagnetism, I'm tempted to suggest we thank the famous Mark Miodownik for a lovely talk, but I'll resist that one. So we have a little bit of time for questions. I think we have microphones. If you'd like to ask a question, just put your hand up and wait for the microphone, because I'd like to record the question as well as the answer. Perhaps I could just take the liberty of asking the first question. So you talked about the lanthanides, and I guess the next row, the actinides. I mean, would you expect them to have very similar properties and behaviors?
The actinides are very interesting because you would think that they might resemble the lanthanides quite a bit. But in fact, there's a big difference in the same F electrons, but sort of one place further down. And what you find is that those early on in the actinides on the left-hand side actually extend out far enough that they do a lot of bonding. And so what they do is they modify the chemistry of elements like uranium and thorium and so on sufficiently to give them really quite distinct things and get them to behave differently from the lanthanides, for example. But as you move to the right, what happens is that the nucleus, the charge is increasing, and what it does is it steadily pulls those electrons back in. And so when you get to the sort of second half, suddenly you find yourself back in a rather lanthanide-like domain. A lot of chemistry has been done with those, but they are all more or less radioactive. Probably the one that you have most day-to-day contact with is americium, americium being the actinide element that sits in the smoke detector in your house. And as one of my neighbors, his house almost burnt down the other day, he didn't have a smoke detector, get one.
Okay, thanks. A question up there.
Hello. Thank you very much. That was a very interesting lecture. Am I correct in thinking in much the same way that the rare earths can turn ultraviolet into visible light, they can also turn electron beams into visible light? I'm thinking of cathode ray tubes. The phosphors in cathode ray
Absolutely.
tubes.
I mean, the rare earths are very widely used in phosphors of all kinds. And really, whether you have UV light or whether you have an electron beam, what you're really doing is you're just kind of shaking the atom's tree in a sense. And what that does is it perturbs those F electrons. And then as they drop down, they emit visible light. So yes, definitely. And the lanthanides are used in all kinds of applications. I mean, some of you, for example, will go to the dentist, and nowadays they have these cunning detectors which essentially take photographs or whatever. You have these X-ray storage plates where essentially you can absorb the energy from the X-rays, get the picture, you can take it somewhere else, and then sort of develop it later or whatever. So there are all kinds of ways in which you can exploit, yes, these electrons in the lanthanides.
Going back to the iterative process of crystallizing and remelting that they were doing in the early days, how do you know when you're done?
Well, that of course was the real problem, because in the 19th century, spectroscopy was in its infancy, and the spectra hadn't been documented. And so, someone would come forward and come to the Royal Institution or the British Association meeting and say, aha, I have a new element, and I'm going to call it aldebaranium or something. There was such an element. In fact, they decided that aldebaranium and Cassiopeium should actually be called ytterbium and lutetium. And of course, there were huge fights. Lutetium Paris should have been named after the French, or should have been named after the Germans. There were huge controversies, absolutely. And I mean, that's the reason why it took so long, was because they had no good way to characterize what they had. And characterization, sort of establishing whether you've got purity and so on, is fundamental to chemistry. And in the 19th century, the tools just weren't there. Now, normally the tool was that you would carry out some selective test. So you could precipitate germanium, say, or rhenium, because there was a special reagent that would do it. But if you have two elements which differ in their properties by only 1.5%, you're in deep trouble. And so these guys just carried on crystallizing, desperately hoping that eventually they would end up with some kind of consistent color or something, and then they would get there. But it was a huge, huge problem. Today, it's easy with a spectrometer.
Question was related in that if Bunsen was using spectroscopy in the 19th century, what did it take till 1940 to discover some of these elements?
Sorry, I missed the question.
Well, Bunsen was using spectroscopy in the 19th century to identify all these lanthanides, yet some of them on your chart went to 1940.
Absolutely. There's one element, and you'll notice, I could skim back, but there was one element, and that's promethium, which was discovered in the 1940s. And promethium, all of its isotopes are radioactive. It's a completely artificial element. There's a quirk of nuclear structure, which means that there are two elements before uranium which only exist in unstable radioactive form. One is technetium, which sits between manganese and rhenium in the transition metals, and the other is promethium, which sits between neodymium and samarium in the lanthanide series. And both of those were discovered essentially through nuclear experiments that were done. Technetium was discovered by Segre, and promethium was discovered by someone else. Segre was Italian.
Who's next?
Thank you. Got some interesting with the use of high temperature superconductor. This seems decades ago, several countries' top scientists kept issue they found the higher temperature superconductor, but suddenly it seems everything just disappeared. No any news come out.
I debated whether or not I should mention the high-temperature superconductors in this talk, because the high-temperature superconductors were discovered in the 1980s, and they were made. They're often called 1, 2, 3 superconductors because you put in 1 smidge of yttrium oxide, you put in 2 smidges of barium oxide, and you put in 3 smidges of copper oxide. You take the whole lot, you grind it all up, you put it in a furnace, and out comes a black ceramic. And the black ceramic looks rather dull until you cool it down to liquid nitrogen temperature. When you get down to below a critical temperature, which is around 100 Kelvin, depends on the precise composition, suddenly they lose electrical resistance. And so Mark Miodovnik, of blessed memory, for example, has regularly done the demonstration here at the RI, in fact, the fact that you can levitate magnets on top. And the rare earths, of course, the first thing they did, yttrium, they said, well, what we're going to do is we're going to make the same thing with lanthanum, we're going to make the same thing with cerium, with praseodymium, with And they went all the way across the series, right, putting in different amounts of these and different fractions, hoping that what they would be able to do was to get a material which was superconducting at room temperature. Progress was incredibly swift for a period of about 5 years. Everyone got hugely excited. And then it kind of tapered off. And the highest temperature that I think they've managed to get to is somewhere between -70 and -80 degrees Celsius. So these are actually quite accessible temperatures where if you can make wires, you will be able to make extremely strong, not permanent magnets of this kind, but permanent electromagnets. And strong magnets of that kind we use for NMR, we use for MRI, all those kinds of things. But all of those tend to operate at liquid helium temperature. So to be able to work in liquid nitrogen would be a tremendous advantage. The real problem is that they're ceramics. And ceramics are a bore because they're not ductile, right? You can't form them into wires very easily. And I think that's one of the things which is really kind of the combination of the fact that they never got the temperature up much further and that they're not very ductile has kind of limited them. But I should also say that there too, although the lanthanide is important, it's the copper which is really the business end, and we don't fully understand how the superconductivity works. But it's the way in which the unpaired electrons on the copper interact, which is what generates this peculiar loss of electrical conductivity.
Thank you. Brilliant lecture today. A pleasure being here. It's about the prices. Why did they crash in 2011? And if one was so inclined, what should one invest in?
Well, I think what you see in this picture is an absolute textbook example of a bubble, right? Is that when China began to restrict exports, and people suddenly realized, in fact, this was almost exactly the same time as when green technology was really kind of getting going. And suddenly people realized that, you needed these things, we couldn't get at them and so on. Everybody piled in. All this sort of smart money went running into this. And they sounded exotic. They sounded different. No one had ever heard of dysprosium, for God's sake, right? And, if you were buying dysprosium futures, you were clearly very clever, right? And people, did make enormous amounts of money, I think, but it's largely a speculative thing. Now, there's no question that, there are restrictions on demand and on supply. What this has really done is it has completely changed the investment environment for sort of producing the rare earths. And one of the things is, why was that mine in California closed down? Well, it turns out that the lanthanides do often crystallize with small amounts of uranium and thorium. And that means that the tailings from the mines are slightly radioactive. And from that mine, you saw the pond down at the bottom. Well, they used to pump the sort of tailing slurry a few miles down the road into an evaporation pond, and they had a whole pile of leaks, and it being, not unreasonably in California or whatever, when you start sort of leaking radioactive stuff, people get panicky. And essentially, the regulatory environment became too difficult, and the company decided that what they would do was go to somewhere cheaper. I think there's an important take-home message here, and that is that, economic drivers, just look at them, are short-term. And we have to think about our long-term strategic interests. And this applies whether you're talking about green technology, whether you're talking about energy security, whether you're talking about climate change. You cannot just leave it to the market because the market is only interested in 2 years, 3 years. 2 years is enough for them to close down a plant and move somewhere else. And then you suddenly discover that there's actually a kind of bigger picture. And so what in fact has happened with that huge price increase and the sudden panic that all of these strategic minerals might be in the hands of a country, that might be a competitor on the world stage in the future, suddenly development is coming on in other places. So in Kenya, there is a mine which is now being explored and considered by people. In India, there are huge deposits and they're starting to develop stuff. The problem is the separation technology is tricky. It's complicated, it's expensive, and of course you've got waste to deal with. And so, it takes time. But there is no question that China's stranglehold, I think, is going to drop, but it will take quite a long time. And, I think the Chinese were absolutely right. Why should they sell this stuff off cheap, right, when they could actually get, more of a share in what they actually, the wealth that they actually have?
So a question in the middle.
Very briefly, can they be recycled?
It's a very good question. Of course they can be recycled. The wonderful thing about elements is that elements are indestructible. And that means that, if you have some praseodymium in something, you should be able to get it back out. The real problem with them is that you only need a tiny smidge in most materials. Now, magnets are one thing. You can always reuse the magnets. You can pull them out. You can smelt them down. But in things like LED lights, fluorescent lights, and so on, the amount of rare earth is so small that actually the economics become very, very difficult. And so there are big efforts. There's a lot of people talking about it. And I think this is a very important issue to do. But in fact, it turns out that it's not tremendously economic to do for many of these applications. And so there are real problems that need to be solved.
So here's one I really should know the answer to, but I can't remember. Going back to the previous question about how do you know when to stop when it comes to the crystallization, at what point did the search for the lanthanides change from being a sort of shooting in the dark to just filling in the gaps? Did Mendeleev predict the force?
Very good. In fact, I forgot to mention Mendeleev. For Mendeleev, the rare earths were a complete nightmare because he didn't know where to put them. He couldn't fit them in the table, right? 5 of them had been found by the time he was building a table, and so he kind of stuck them in somewhere where things went 3+, and then went, and kind of left it at that. And this was a real problem because no one knew where these building blocks went into the periodic table. And it wasn't, of course, until Moseley had established what atomic number was that things began to fit together, right? And suddenly they realized there couldn't be more than 14. And then as the quantum mechanics rules came through, it became clear, right, that was essentially, you'd found the whole lot. There was the gap, of course, in promethium, and so that became a target. But essentially that was it. And there's one other thing that I think I should mention as an Italian this evening. And I'm grateful to Alex Jah for reminding me. This is my grandmother's copy of Il Sistema Periodico by Primo Levi, which is the most astonishing work of chemical literature ever. If you haven't read it, go out and steal a copy immediately. Fortunately, my copy is in Italian, and I hope there aren't too many people who want to read it, the original tonight. But in the book, Primo Levi, about halfway through, has a chapter on the element cerium, about how, when he was at Auschwitz as a prisoner, and he had certain privileges because he was a chemist, and he'd been allowed to do certain technical tasks. He was rooting around in a storeroom, and he saw some little rods of a strange, dark material that were unlabeled. He didn't know what it was, but he thought, kind of neat. The Germans don't leave anything unlabeled. This must be something valuable. And he grabbed 3 bottles of it, shoved them in his pocket, went off, and he and his friend Alberto started tinkering around with them, trying to figure out what they were. And they hit them, and they had no equipment, and they suddenly realized that they sparked. And he realized, it's ferrocerium. It's this stuff. And so they laboriously cut them up into little pieces, and they were able to sell them to fellow prisoners in exchange for food. And the reason that Primo Levi survived Auschwitz is thanks to this stuff.